A siren wails over Orting, Washington, and every child in town starts walking uphill. They have done this since kindergarten. It is not a fire drill. It is a lahar drill, a rehearsal for the day. A wall of mud and ice comes down the valley. Roughly 80,000 people live on top of old mud flows from a single mountain 59 miles from Seattle. Everyone assumes the danger is an eruption. It isn't. Mount Rainier has already buried these valleys twice without erupting. The same trap has fired for 5,600 years. In Orting, the countdown clock is 40 minutes. That number is not a scare tactic. It is roughly what emergency planners and the United States Geological Survey work with when they model how fast a wall of mud could travel from the mountain to the town. And here's the part that takes a while to sink in. The eruption everyone pictures, the ash column, the lava, the red glow on the horizon, is not the thing most likely to kill people in the Puyallup and Carbon River valleys. The thing most likely to kill them is the mountain quietly falling apart. Possibly on a clear day. Possibly with no warning from below at all. Stand in downtown Seattle and look southeast on a cloudless afternoon. And Rainier does not look like a threat. It looks like a postcard. 14,410 feet of white symmetry floating above the skyline, close enough to feel like a neighbor, and far enough to feel harmless. That distance is the first thing the mountain gets you to misread. 59 miles sounds like a safe buffer. It isn't, because the danger from Rainier does not travel through the air. It travels through the ground, down the exact river valleys that carry commuters, schools, warehouses, and whole towns back toward the peak. Look at those valleys on a map, and the problem becomes obvious. Rivers radiate off the mountain like spokes. The Puyallup, the Carbon, the White, the Nisqually. They carved deep, flat-bottomed corridors down to the Sound. And those corridors are where the flat, buildable, fertile land is. So that is where people built. The rivers that drain the mountain are also the ramps that carry the mountain when it decides to move. Everything valuable in this landscape sits inside a chute pointed straight at the summit. And the chute does not end at some rural outpost. Follow the Puyallup down and it runs through Orting, then Sumner and Puyallup, then into the industrial tide flats of Tacoma, and the port on Commencement Bay, one of the busiest cargo gateways on the west coast. Much of that low, flat, built-up ground, the warehouses, the rail yards, the container terminals, sits on sediment that a lahar delivered from the mountain in the geologic past. The port is on the delta the mountain built. When planners talk about the hazard zone, they are not describing a stretch of forest. They are describing a corridor of towns and infrastructure. With roughly 80,000 residents living inside it, plus everyone who drives in to work each day, here is the fact that reframes everything else. Mount Rainier carries more glacial ice than any other mountain in the lower 48 states, more than a cubic mile of it. As much ice as all the other Cascade volcanoes combined, Hood and Adams and Baker and the rest, stacked onto one peak. More than 24 named glaciers hang off its flanks. From a distance, that ice is the beauty. To the people who study this mountain, that ice is the ammunition. It just needs something to launch it. And this is not a dead mountain that merely happens to be tall. Rainier is an active volcano, quiet but warm. Heat still leaks from its summit, enough that vents near the top keep a network of caves melted open inside the summit craters. Hollow rooms of ice, sitting on ground warm enough to steam. That internal heat matters, and we will come back to what it has been doing to the rock for thousands of years. It is also part of why scientists take this particular peak so seriously. Rainier is one of a short list of volcanoes worldwide singled out decades ago for intensive study, not because it is the most explosive, but because of the brutal arithmetic of what sits below it. A dangerous mountain in an empty wilderness is a scientific curiosity. A dangerous mountain leaning over the largest metropolitan area in the Pacific Northwest, home to nearly 4 million people, is something else entirely. That something is not always fire. Sometimes the mountain is the trigger for itself. And to understand how a volcano kills without erupting, you have to stop thinking about the summit as solid rock. Because in places, it isn't. Not anymore. But start with the people who understood the valleys first, long before anyone drilled sensors into the ice. The Puyallup and Nisqually peoples lived along these rivers for thousands of years. They had a name for the mountain long before it carried the name of a British naval officer who never set foot on it. To them, it was Tahoma, or a name close to it, the great snow-covered peak that fed the rivers. And their relationship with the low ground was practical, not sentimental. The rich soil in the valley bottoms, the same flat farmland that later drew settlers, was rich because it had been laid down by the mountain in violent pulses. Living with Rainier meant respecting where you camped and understanding that the rivers could carry more than water. That was knowledge earned the hard way, over generations, and it was correct. We can prove it was correct because the ground itself keeps the receipts. Roughly 5,600 years ago, the summit of Mount Rainier collapsed, not a piece of it. A huge section of the upper mountain came apart and rushed downhill as one of the largest debris flows the region has ever recorded. Geologists call it the Osceola mud flow. It carried on the order of a cubic kilometer of rock, ice, and mud, filled the White River Canyon to depths well over 300 feet in places, and did not stop until it reached the lowland at the edge of Puget Sound. It buried the ground where Enumclaw, Auburn, Kent, and part of the Puyallup Valley now sit. Tens of square miles of what is now suburbia are built directly on top of that single event, and it did not just bury the lowlands, it decapitated the mountain. The collapse tore away something like the top 1,500 feet of the summit, lopping the peak down from a former height well above 15,000 feet to roughly what we see today. The Rainier on the horizon now is a beheaded version of the one that stood there before. The missing top of the old mountain is, in a real sense, the ground under those neighborhoods. Sit with that. The strip malls, the school districts running today's evacuation drills, the families asleep in the valley tonight, are standing on the debris of the last time the top of the mountain fell off. The disaster zone is not a hypothetical line on a hazard map. It is the foundation. An eruption was likely involved in the Osceola collapse. But that raised a harder question that took geologists decades to answer. The volume that moved was enormous, and it moved fast, and much of it was already weak, water-soaked material before anything pushed it. The summit did not need to be blasted apart. It needed to be nudged. So what made the top of a mountain that fragile in the first place? The next piece of evidence made that question urgent because the next collapse did not clearly involve an eruption at all. About 500 years ago, give or take, the west side of the mountain let go. This one is called the Electron Mudflow, named for a small community in its path. A slab of the upper west flank broke loose and poured down the Puyallup drainage. It was smaller than Osceola, but it still buried roughly 13 square miles of the valley, in places more than 25 feet deep, and it ran all the way down toward where Orting and Sumner sit today. Investigators found whole, standing forests snapped and entombed in it. And here is where the mountain stops being a history lesson and starts being a live problem. The electron mud flow shows little sign of having been triggered by an eruption. No clear ash, no obvious blast, no volcanic fingerprint on top of it. The best available evidence points to the flank simply failing. The mountain collapsed cold, possibly on an ordinary day. That is the reversal that changes the entire story, because it means the thing people watch for, the eruption, the tremor, the smoke, may never show up before the disaster arrives. If the trigger is not fire, then every warning system built to detect an eruption is watching the wrong door. So what actually weakens the rock? This is the part that took real science to uncover, and it is the quiet engine underneath the whole nightmare. Mount Rainier is not a dead pile of stone. It has a hydrothermal system, hot fluids, and acidic steam circulating through the upper mountain, heated from within. Over long spans of time, those fluids chemically attack the volcanic rock. Hard andesite gets cooked and dissolved and converted into soft clay minerals. The rock does not just crack, it rots. It turns into something closer to wet modeling clay, saturated with water, slick, and heavy. USGS scientists mapped where this altered rock is concentrated, and the answer is exactly where you would least want it. Large volumes of it sit high on the mountain, especially on the upper west and northwest flanks, the same side that produced the electron collapse. This is why researchers keep pointing at the Puyallup drainage as the most likely path for the next big one. The ammunition is the ice. The fuse is a chunk of summit that has been softening from the inside for centuries. You can even see the scars of this process. On the upper west side of the mountain sits a vast cliff-rimmed bowl called Sunset Amphitheater, a place where large amounts of that weakened, clay-rich rock stand exposed and unstable. Geologists who sampled the debris from the old flows found it loaded with exactly the minerals that form when volcanic rock is cooked by acidic fluids, clays, and altered fragments that are the chemical signature of rot. That is how they know the ancient collapses began with pre-weakened rock, rather than fresh, solid stone blown apart by an eruption. The mountain has been quietly preparing the next slide for a very long time, and it left its fingerprints in the mud of the last ones. And clay does not need a volcano to fail. It needs gravity, water, and time, all of which the mountain has in abundance. This is why a Rainier lahar can start with no eruption. A large earthquake could shake the weakened flank loose. A stretch of unusually heavy rain could saturate it past its limit. Or a slab could reach the end of its own strength and go, the way the electron flank apparently did, with no announcement at all. If that sounds like a slow-motion structural failure waiting for an excuse, consider what the mountain has done in living memory without collapsing at all. On the 2nd and 3rd of October in 1947, heavy autumn rain sat over the mountain and did not let up. On the south side, in the Couts Creek drainage, the water combined with loose glacial debris and generated the most voluminous debris flow of the historical record on Rainier. Tens of millions of cubic yards of mud, rock, and shredded timber grinding down the valley. It buried the park road under close to 30 feet of debris. No eruption, no collapse of the summit. Just rain, ice-fed water, and a slope full of loose material, doing in a single storm what geology usually takes an age to accomplish. 1947 is close enough to touch. There are people alive who remember the road being gone, and it proved something the ancient mudflows only implied. You do not need the mountain to fall down, and you do not need it to erupt. You need weather. The trap does not have to wait for a rare catastrophe. It can fire on a bad week in autumn. 16 years later, the mountain proved it does not even need the rain. On December 14, 1963, high on the east side, a large mass of rock broke away from the crumbling flanks of Little Tahoma Peak, the jagged remnant that juts off Rainier's eastern shoulder. It came apart in a series of at least 7 separate rock avalanches, roughly 14 million cubic yards of shattered stone in total, and they poured down onto the Emmons Glacier and kept going. These avalanches did something that should not be comfortable to picture. They moved so fast, an estimated 80 to 90 miles an hour, that they rode on a trapped cushion of compressed air beneath them, nearly frictionless, skating down the valley. They ran more than 4 miles from where they started and dropped over 6,000 feet in elevation before they finally stopped, less than half a mile from the White River campground. Half a mile. In December, the campground was empty, which is the only reason that event is a footnote and not a body count. Investigators later suspected the trigger may have been nothing more than a small steam explosion near the base of the peak, the mountain's internal heat popping a weakened chunk of rock loose. No eruption, no storm. A quiet, cold day in December, and 14 million cubic yards of the mountain nearly reaching a place where people sleep in summer. It was one of the largest rockfalls ever documented in the Cascades, and almost no one was there to see it. So is this ancient history, or is it happening now? The uncomfortable answer is that a smaller version of the process runs almost like clockwork. On the mountain's southwest side, the South Tahoma Glacier has produced a long series of what geologists call outburst floods. Water builds up inside or beneath the melting glacier, then suddenly releases, bursts out of the ice, picks up loose sediment, and turns into a debris flow that charges down Tahoma Creek. Since the late 1960s, more than 20 of these have come down that one drainage. They have chewed a gorge over 100 feet deep into the sediment below the glacier. In 2019, one of them sent boulders and a slug of muddy water down the valley and forced the closure of a park road, again, with no eruption, no earthquake, nothing exotic. Just a hot stretch of summer melting the ice a little too fast. That is the part that should get your attention. These outbursts cluster during unusually hot or rainy spells. They are the mountain clearing its throat. Small, local, mostly hitting empty backcountry, but running on the exact same script as the monsters. Ice plus water plus loose, weak material, moving downhill faster than a person can. The system is not dormant. It is idling. And it does not idle rarely. In the roughly 10,000 years since the last ice age released its grip on this landscape, Mount Rainier has sent dozens of lahars and debris flows down these valleys. Geologists count on the order of 60, with the largest valley-filling flows arriving, on average, every several centuries to 1,000 years or so. That average is not a promise of safety. It is a reminder that the last really big one, the electron mudflow, was about 500 years ago, which places us somewhere in the middle of the window rather than at the start of it. Averages do not schedule the next event. They only tell you the machine has done this many times before and shows no sign of having stopped, which raises the obvious question. If the mountain is this active, if the flank is this weak, if the valleys are this loaded with people, who is watching? And how much time would anyone actually get? To understand why anyone bothered to wire a mountain for sound, look at what happened on the other side of the equator on the night of November 13, 1985. A volcano in Colombia called Nevado del Ruiz produced a modest eruption, nothing enormous, but enough to melt part of its summit ice. The meltwater gathered into lahars and funneled down the river valleys in the dark. One of them reached the town of Armero, more than 40 miles down the valleys, hours after the eruption began. The town had received confused, conflicting guidance and largely stayed put. The lahar buried it. Around 23,000 people died in a single night, most of them while they slept. Read the details of Armero, and the resemblance to Rainier is almost unbearable. A snow and ice-capped volcano, a modest trigger that mobilized the ice into mud, river valleys acting as channels, a town on the flat ground at the end of a channel, far enough away to feel safe, close enough to die. And a warning problem that was not really about detection, but about time and belief. Armero is the ghost standing behind every Rainier hazard map. It is the proof that this exact chain of events is not theoretical, and it is why the agencies around Puget Sound stopped treating a Rainier lahar as a geologist's abstraction and started treating it as a countdown. The watching part is real, and it is genuinely impressive. In the mid-1990s, after the USGS made clear that a large lahar could happen without an eruption, Pierce County, the USGS, the state, and other agencies built a lahar warning system for the Carbon and Puyallup valleys. It went operational in 1998, and it has been upgraded steadily since. The core idea is simple and clever. A lahar is not silent. A river of mud and boulders makes the ground shake in a very specific way as it grinds downhill. So they buried sensors that listen for that ground vibration, feed the signal to computers that can distinguish a lahar from an ordinary earthquake or a passing truck, and, if the pattern matches, automatically trip a network of sirens. Those sirens run down the valley from Orting toward the port of Tacoma. When they sound, everyone in the zone is supposed to do exactly what those school children rehearse: stop and climb to high ground on foot. The technology behind those buried sensors was not dreamed up in the abstract. It came out of Mount St. Helens, 50 miles to the south, which erupted in 1980 within view of the same cities and sent its own lahars racing down the Toutle River, ripping out bridges and burying valleys. That eruption taught Cascade scientists two things that shape Rainier planning to this day: that these volcanoes produce killer mud flows even in relatively small events, and that a flow's ground vibrations can be detected and used to sound an alarm ahead of the wave. The instruments first developed to watch flows off St. Helens were adapted and placed on Rainier. The mountain that taught the lesson is close enough to see from the mountain now being watched, on foot. That phrase is doing a lot of work, and it points straight at the limit of the whole system, because detection is not the same as escape. The sensors can catch a lahar early. The sirens can fire within moments. And it still might not be enough because the flow is faster than the traffic. A large lahar can travel at 45 to 50 miles an hour where the valley funnels it, and it can pile up dozens of feet high, tall enough to swallow a 2- or 3-story building. In a town like Orting, sitting on the flat valley floor where the Carbon and Puyallup drainages meet, the modeled arrival time is short, on the order of 40 minutes to under an hour from the moment a flow starts high on the mountain. And Orting has a single road problem. The bridges out of the low ground can jam within minutes. A family in a car, in a line of cars, is a family in the path. And a lahar is not a flood you can wade through or swim out of. Picture wet concrete moving at highway speed. A mature lahar is a churning slurry of mud, sand, and rock, dense enough to float and carry boulders the size of cars, and whole trees torn out by the roots, scouring the valley down toward bedrock at its leading edge. It does not lap at a doorstep and recede like river water. It fills the valley, buries what it hits, and then, as it slows and the water drains out of it, it sets, hardening into a field of rock and mud that can entomb a house to the second floor. That is why the old flows are still readable in the ground thousands of years later. And it is why survival here is almost binary. You are either above it when it passes, or you are inside it. There is very little in between. That is why the town's most talked about safety project is not a wall or a dam. It is a bridge for people to run across. Orting has pushed for a dedicated pedestrian evacuation bridge, a roughly $9 million structure whose entire purpose is to let residents, and especially school children, cross the river valley on foot and reach the hillside before the mud arrives. Think about what that represents. The most realistic plan for saving the town's kids from a volcano is to help them outwalk it to the nearest high ground. Not outdrive it, outwalk it. Because the roads cannot be trusted to clear in time. None of this is guesswork bolted together by nervous officials. The USGS is blunt about the core problem. A Rainier lahar cannot be reliably predicted, but it can be simulated, and the simulations are not reassuring. In recent modeling of exactly the scenario that worries them most, a landslide-driven lahar starting on the weak west flank and pouring into the Puyallup drainage, was Wasanadikya. Scientists traced how such a flow would accelerate, bulk up with sediment and water, and run down the valley toward the towns. The models are how planners arrived at the arrival times that set the sirens and the drills. They are, in effect, rehearsals run on a computer for a rehearsal run on foot. And the foot rehearsal is enormous. Once a year, the valley communities run a coordinated lahar evacuation drill, and it is not a token exercise. Tens of thousands of students across multiple school districts, Puyallup, Sumner-Bonnie Lake, Orting, White River, Carbonado, leave their classrooms on cue and physically walk their assigned routes to high ground, dozens of schools moving at once. It ranks among the largest volcano evacuation drills anywhere in the world. Think about what it means that a region needs the largest volcano evacuation drill on Earth. It means the people who study this mountain most closely have looked at the numbers, accepted that they cannot stop the flow or reliably see it coming, and concluded that the only real defense left is to make sure an entire generation of children knows the way uphill by heart. So the reversal at the heart of the modern era is this: we can now hear the mountain coming. We built the sensors, the software, the sirens, the drills, the maps, the bridge. And none of it changes the one number that matters most: the distance between the people and the high ground, divided by how fast they can move. The signal can arrive perfectly and still arrive too late for anyone caught in the wrong place. Technology solved the problem of knowing. It did not solve the problem of being there. And if you want proof that the ice on this mountain does not care how prepared or well-equipped a person is, you do not have to imagine the lahar. You can look at the people who go up onto the ice on purpose, with the best gear and the best guides in the country, and do not come back. On June 21, 1981, a guided party of 29 people was climbing the standard route toward the summit, moving up across the Ingraham Glacier before dawn, the way thousands do every year. This was a commercial climb run by the mountain's main guiding operation, Rainier Mountaineering, one of the largest guided parties on the peak that day, full of clients who had trained for it. High above them, a wall of glacial ice, roughly 100 yards wide, broke free. A serac collapse, a block of the glacier simply reaching the end of its structural life and letting go. It swept down onto the climbers and drove a group of them into a deep crevasse. 11 people died, 10 clients, and 1 guide. It remains the deadliest mountaineering accident in American history. There was no mistake to pin it on. A National Park Service Board of Inquiry examined the event and concluded it was essentially an unpredictable, random collapse, the kind of thing the glacier does on its own schedule, indifferent to who is underneath. The guides were not found to blame, and the bodies were never recovered. The crevasse that swallowed them was too deep and too unstable to dig into safely. The victims are still up there, entombed in the moving ice, carried slowly downhill inside the glacier itself. The same ice that would feed a lahar had already made 11 people part of the mountain. More than 3 decades later, the ice did it again, in a way that was almost the opposite in style and identical in outcome. In late May of 2014, a party of 6 set out on Liberty Ridge, one of the hardest and most exposed routes on Rainier. 4 clients and 2 guides from a respected Seattle guiding company, led by 2 men, Matt Hegeman and Eitan Green, who between them had serious experience on the mountain. Their last contact was a satellite phone call from around 12,800 feet reporting that they were making camp for the night. Then nothing. When searchers went in, they did not find survivors. A helicopter crew, flying over terrain far too dangerous for climbers to search on foot, picked up the faint pulses of the party's avalanche transceivers coming from the ice at the base of a wall, roughly 3,300 feet below the team's last known position, along with scattered gear. That was as close as anyone could get. The evidence points to the whole team being swept off in the night, most likely by falling ice or rock or an avalanche off the face above them, though the exact sequence has never been confirmed. It was the deadliest event on the mountain since 1981, and once again the recovery was judged too dangerous to attempt. The face above sheds rock and ice more or less continuously. Sending a ground team down into it would only have risked adding names to the list. 6 people went up, and the mountain kept them. Notice what those 2 events have in common across 33 years and completely different routes and skill levels. Best guides, modern gear, beacons, satellite phones, trained response. And in both cases, the ice moved on its own timetable, killed without warning, and could not be undone or even reached afterward. The mountain did not negotiate with preparation. That is the same ice, the same instability, the same indifference that hangs above the sleeping valley towns waiting for the flank to give. So put the whole system together, because that is the only way it makes sense. The geography sets the trap. Steep radial valleys carry everything, water, sediment, disaster, straight down to where the flat, buildable land is, which is exactly where people settled. The ice supplies the volume and the punch, more than a cubic mile of it, ready to melt and mobilize the instant something violent starts. The rock supplies the fuse, an upper west flank chemically rotted into weak, saturated clay by the mountain's own internal heat, capable of failing under an earthquake, a heavy rain, or nothing obvious at all. The weather supplies the routine trigger, the storms and hot spells that have already produced debris flows in 1947, in the Tahoma Creek Gorge since the 60s, and as recently as 2019. Human motive supplies the exposure, and this is the cruel knot at the center of it. The valleys are dangerous for the exact reason they are valuable. The flat, rich ground that draws farms and towns and industry is flat and rich because past lahars flattened and enriched it. People did not build in the path by accident. They built there because the path is where the good land is. The same process that threatens the towns is the process that created the places worth living in. Every warehouse on the Tacoma Tide Flats and every house in Orting is a bet that the mountain will hold still for one more generation. Technology supplies the illusion of a solution. Sensors, sirens, models, drills, and a bridge built so children can run for the hills. All real, all useful, and all bounded by physics. Detection changed, distance did not. The mountain can be heard coming and still arrive before the valley can empty, and history supplies the verdict. This is not a maybe. The Osceola flow proved the summit can collapse and reach the sound. The electron flow proved it can happen without an eruption. The 1947 storm and the 1963 rockfall proved weather, and the mountain's own heat can move enormous volumes in the modern era, one of them stopping half a mile from a campground. The Tahoma Creek outbursts prove the machine still runs. The climbers on the Ingram and on Liberty Ridge prove the ice kills on its own schedule and keeps what it takes. And Armero, on the far side of the world, proved that the last step in the chain, a town full of sleeping people at the end of a valley, ends exactly the way the hazard maps say it will. Same trap, different eras. The same underlying failure playing out again and again while the technology around it improves and the fundamental exposure does not. There is a warming thread running under all of it, and it deserves honesty rather than hype. As the climate warms and the glaciers thin and shift, the loose sediment they leave behind and the melt water they release can feed exactly the kind of outburst flows that Tahoma Creek already produces. It is fair to say the mountain's plumbing is changing. It is not honest to promise that this means a single clean increase in danger on a known date. What is certain is that the weak rock is still weak, the ice is still loaded, the valleys are still full, and the clock in Orting still reads about 40 minutes. Which brings it back to a quiet morning on the mountain. A sensor sits buried in a valley high on the flank, blinking, listening to the ground, waiting for a vibration it can recognize. Miles below, an evacuation route sign points uphill, away from a school, toward the ridge. The altered rock on the west face keeps softening, one wet season at a time, on no schedule anyone can read. And when the drill ends, the children of Orting walk back down off the high ground, back into the valley, back into their homes, on top of the last disaster, because that is where they live. That is where everyone lives here. And the mountain, patient and white and beautiful on the horizon, keeps holding its cubic mile of ice and waits.